All right, everyone. I guess we can start. So thank you all for waking up early and coming to this tutorial. So when Vasilis and I did this, we realized that this tutorial is actually scheduled at the same time that they have the Turing Award lecture for deep learning. So we really appreciate the fact that you guys are all here, and this is a really great turnout. All things considered. So
But you didn't realize that you're free to go to the
yeah, exactly. If you didn't realize that, feel free. Okay, so okay, good. So what we're going to talk about is we're going to give a brief tutorial about some AGT challenges that we identified in opportunities in deep learning. Okay. So basically, the premise, as you guys probably know if you've been alive for the past few years, basically is that noise can cause misclassification in state-of-the-art machine learning models. This is one challenge. And the other challenge is that data can be synthesized to appear real, right? And this is the challenge that is associated with things like deepfakes and also GANs. Okay? So as we're kind of going to discuss today, many of these problems that arise, whether due to noise or kind of these issues with GANs, inherently they're actually they involve game theory at a fundamental level, and this brings kind of fundamental challenges and opportunities for us as a community. So what Vasilis and I kind of thought is we thought it'd be interesting to sort of just kind of introduce some of these kind of the basics behind adversarial noise and also GANs, in the hopes that we can, as a community, we can basically think about these problems together. And we're going to throw some problems that we think are interesting, but I think that all of us will kind of together will find like interesting problems and interesting solutions that can, one, bring this field forward, and two, that will basically also kind of advance kind of our applications of game theory. So in this tutorial, what we're going to do is I'll start by talking about the first part, which is adversarial noise, and then we'll take a break, and then Vasilis will talk about the second part on basically on GANs. Okay. All right. So for the first part, we're going to talk about robust classification in adversarial noise. So the main pain is that adversarial noise can cause misclassification. So this is interesting because basically with the advance of deep learning, we've seen that machine learning can really perform outstanding results, right? Achieving like very, very high accuracy for images, for example, but also voice and other types of data. But in 2014, a paper that came out of Google showed a very interesting phenomena about about deep learning models and also just in general about classification, is that basically what you can do is you can introduce a little bit of noise to your data, and that causes a state-of-the-art classifier to misclassify that data point. So in this example, on the left, we have an image of a bus. We can all see that this is a bus, and we feed it to a neural network, and the neural network that was trained on something like ImageNet or CFAR will tell us that this is a bus. Okay? But it turns out that what you can do is you can create noise. So this is the noise here that we see in the middle image. Okay? And you can add that noise to this image of a bus. And now once you've added that noise, we get a picture on the I guess it's your left, right? And that image still looks like a bus to us, but now the neural network thinks that this is an ostrich. Does that make sense? So this is what we mean by adversarial noise. Yeah?
When you say this is noise,
right.
It looks like noise to humans, but presumably it's actually very structured in some way.
Yeah, exactly, right. So, we use the term adversarial noise, so I guess to differentiate it from what we think about as noise, right, something that comes from a distribution. So the terminology is adversarial noise. I agree. This is the terminology that somehow people use, but I agree that it's highly structured, and we're going to see pretty soon like that it's very highly structured. It very much differs from noise in the way that we think about noise. But I totally agree. Right, but basically, but that's the idea. We can add highly structured noise right to an image, and then cause the neural network to misclassify it. So this matters because there are problems where kind of we are making critical decisions based on classification, right? So kind of like an obvious one, if you believe in self-driving cars, is that when we give classifiers that are trained to basically identify road signs, then now adding noise to these road signs can actually change the classification of these road signs, right? And that could just immediately lead to dangerous outcomes, right? And kind of there's been more work where you can actually show. You probably have already seen this on the news, or basically you can actually take physical stickers, you put them on road signs in such a way that actually causes neural networks and other classifiers to misclassify these road signs, right? So this is an inherent danger. We want to understand kind of the properties of this highly structured noise, right? And also basically kind of our goal is to ultimately, right, is to understand how to build classifiers that are robust to these sort of attacks. Make sense? Okay, great. All right, so so what I'm going to talk about is I'm going to talk about, first of all, I'll kind of like define what adversarial noise is, and then I'll kind of like formulate this to you as a two-player zero-sum game, right? This sort of like game between ruleless classification and adversarial noise. Then we'll talk about robust optimization for non-convex objectives and adversarial training, and then I'll just mention things like black box attacks and like randomized smoothing, which are kind of more recent things that came out. Okay, so just to begin with, so the question is, like, what is adversarial noise, right? So before we kind of go into adversarial noise, let's just sort of agree what is classification. So classification is, we basically think about this as a separation between data points, right? So we have our data points of the bus, feature, and we map them into some feature space, and data points of an ostrich, we map those into feature space. And kind of a classic way of classification is basically to draw a line, right, between these points in the feature space, right? And anything that falls below that line, we say that this is going to be a bus, and anything above that line, we're going to say that this is an ostrich. So what adversarial noise does is basically, we can think about this as basically pushing a point beyond the decision boundary, right? So we take our data point that's classified as a bus, we add some noise to it, and now that we've added noise to that point, it goes across the decision boundary. It still looks like a bus to us, right? But now the classifier thinks that this is an ostrich because it got classified in that region. Okay? And this is not only true for linear classifiers, this is also true for neural networks, right? Where an attack is basically pushing a point beyond the decision boundary. But now for neural networks, it's these sort of, an attack is somehow somewhat trickier because neural networks have all these sort of, like they're basically manifolds and have like all these pockets, and you have to sort of understand how to push that point across the decision boundary. Okay. All right. So basically, kind of slightly more formally, generating an adversarial noise is an optimization problem. So how is this an optimization problem? Really what we're doing is, to find adversarial noise, we're solving either one of two problems. The one on your left is for untargeted attacks, and the one on the right is targeted attacks, right? So a non-targeted attack is an attack where basically what I do is I only care about the fact that I'm misclassifying my data point, right? So that it doesn't get classified as the correct label, right? But in a targeted attack, I actually care about the label, in this case L, right? That I'm actually targeting. Okay. So basically, these optimization problems, right? They basically involve we want to minimize the norm of the noise, right? We intuitively want to make the noise as small as possible so that it's still close to the original image, under the constraint that now the decision F of the classifier has it mislabeled, right? And adding this noise to the data point is still a valid point. It's still a point in the 0-1 hypercube.
Question?
Yeah.
Do you need access to that?
Okay, that's a great question. So in this case, so everything I'm going to talk about for like if this tutorial is 45 minutes, for 44.5 minutes, I'll talk about I'll assume that you have access to F, right? And then in the last 30 seconds, I'll also talk about what's called black box attacks, where you don't have access to F, and these are also these are very interesting cases, right? Kind of like I guess the rationale for having access to F is because we want to assume that, right, like kind of the adversary is omnipotent, right, and we want to know how to train like the best possible classifiers against a very strong adversary. Okay? But that's a great point of whether we have access to the classifier or the F or we don't. Okay? And I'll talk about it kind of like more implicitly. We're gonna not exactly assume, we're not always going to assume that we have like access to F, but maybe like the loss function that's used to train the classifier. That's more accurate. Okay. And now kind of there are typical choices for the norm, right? We want to select like the smallest. We say we want to select intuitively like the smallest amount of noise, right? So small under what norm? So a typical norm is like the L infinity norm, which kind of guarantees that each feature is perturbed by like some sort of small epsilon, right? But other norms that are popular are like the L2 norm, or I think it's like the L infinity norm, and the L2 norm are the most well studied. Okay. Okay. So when we're looking at linear classifiers, the question of what is the optimal noise is a pretty straightforward. There's a pretty straightforward solution to that. For linear classifiers, the optimal noise basically means that we're taking a point and we're projecting it on the hyperplane, right? And by doing that, we're basically kind of creating misclassification because the point goes beyond the decision boundary, right? So that would be the kind of the minimal noise that we can add so that we can create misclassification. Does that make sense? Yeah. Whenever we have neural networks, then we're no longer living in a world where necessarily the spaces are convex, right? So now there are different methods, right, for finding what is kind of optimal noise. Okay? So the first method for kind of defining what is kind of like quote unquote the best noise is what's called the fast gradient method, and this is the method that was proposed by the original paper that introduced this problem of adversarial noise, right? And basically, what we do is kind of we look at the gradient of the point, right, and we push it according to the sign. We push it in some sort of epsilon. We push in that direction, kind of like in an epsilon radius. Okay? After that, there have been kind of other methods like the kind of iterative fast gradient method, which basically does this sort of process, but iteratively, so it does kind of like this iterative search, right? Kind of where to push the point, where to kind of like push the point so that we can create an adversarial example. And then, and finally, there's kind of more recently, there's been this method of deep fool, which basically tries to kind of generalize this idea of projecting a point not to, basically to the manifold, okay? Even though the spaces are not convex. And then kind of when you try these different methods, then you can have a visual comparison and you can decide for yourself maybe like kind of what looks better to you. So on the top we have deep fool. This is from the deep fool paper. So this image is an image of a whale apparently, and by adding noise to it, you make it into a turtle. Okay, and then below it is the fast gradient sign method, right? Which we can see that just visually, if you kind of zoom in, then maybe you notice that there's slightly looks noisier. The fast gradient method slightly would look noisier on this image. So in general, there because the spaces that neural networks create are non-convex, right? We don't have kind of guaranteed methods that will converge to create like an optimal attack, right? And kind of finding the best attack is still it's an ongoing question. There's been a recent line of work on kind of simpler neural networks where you can prove guarantees. So for example, 2-layer neural networks, right? And an interesting challenge, this is more of an optimization question, is whether one can show that kind of design an optimal algorithm for creating adversarial noise whenever your classification is like a simple 2-layer network. Does that make sense? Right. So this is kind of an interesting challenge for kind of an algorithmic or kind of an optimization challenge. All right. So that's kind of so this is kind of like a brief overview for what is just a simple attack, right? Or simple adversarial attack, and how do we get these images misclassified? So what I kind of want to maybe like the interesting thing to us is going to be more about robust classification as a zero-sum game. Okay. So one obvious defense, if I sort of asked you, right, like what is an obvious defense you think against adversarial noise? Would anybody have kind of any suggestions? Okay, so all right, so one kind of like, well, I mean, maybe what I'm writing here is not the obvious idea that you have, right? This is your chance to be creative. Okay, you don't want to take it. Okay, good. So right, so kind of like one obvious defense is basically you retrain your classifier given the noise, right? So basically, if we have like the noise vector is like if we kind of like think of the noise as the adversarial noise as a function, this is R, right? It takes a data point xi and maps it to like the perturbed point, right, which gets the classifier, the original classifier creates misclassification. So what one can do is basically apply that transformation on all the data points, right, and then retrain the classifier, right, with that noise.
So,
yeah.
So that assumes that you know R, but you know the function R.
Exactly, right. So if I kind of go to NIPS and I read a paper about an adversarial attack, right, and I can like as a learner I can say, well, maybe I'm not going to be bothered by this attack because what I could do is I will just go and I'll retrain my classifier using that attack, right? So somehow, like if you know, right, if you know what the adversary is going to do, right, then it's easy for you to defend against, right? And right, intuitively, right, this is and empirically this works really well, right? And why? Well, intuitively, right, this works well because we know that the kind of the adversarial noise basically perturbs the point to a place where the point appears to be from the same distribution, right? So somehow now retraining the classifier when the points are perturbed is gonna give us a good kind of still a good classification because we believe that that these neural networks, they know how to generalize well, right? So that's kind of an idea for why this works well. So now, kind of given this mindset, given that the learner knows kind of how to defend against a particular strategy of the adversary, then this sort of brings up a kind of a zero-sum game, right? So this is a zero-sum game in the following way. So since the adversary knows that the learner can retrain the classifier, right? What the adversary can do is basically they can randomize over different attacks, right? So you can think of an adversary that also goes to NIPS or ICML, right? And maybe even ICLR, right? And reads all these different papers about these different attacks, right? And basically what they do is they can now randomize between all these different types of attacks, right? And now you can imagine a learner that's sitting in this audience and kind of hearing that the adversary can do this. So now what the learner can do is the learner can basically go ahead and kind of retrain against every possible attack, right? And then as a strategy, that learner can randomize, right, between these different classifiers. Yeah?
I don't understand why the adversary can't attack the retrained network.
The adversary it can, right? And
this seems to be a sort of arms race.
It is, right? I mean, and this is why it sort of lends itself, right, as a we think it lends itself as a kind of as a two-player zero-sum game.
But there are an unlimited number of strategies.
I mean, that's true, and isn't it? But when did that and then this is why it's interesting. Like this is why sort of like this, it brings up non-trivial, right, challenges in AGT, right? We never said that there have to be finitely many strategies, right? And there are some cases where we know how to deal with infinitely many strategies in zero-sum games, right? But these are exactly why these things are interesting, and they're interesting like to our community because like we have the kind of potentially we have the the tools and kind of the mindset to attack these sort of challenges. Yeah.
So how is this better than like the John Bucci and his students' approach of you expand, you take noise to be a certain ball,
Yeah.
and you like sort of say that I want to find the max min classifier over the entire ball. So not moderate as a zero-sum game, but more as like a standard min-max problem.
So okay, so the question is how is this better than a technique proposed by Ducci et al. I guess, where the idea is basically you take a data point, you look at all the points around that data point, kind of in an epsilon ball around it, right, and you solve the max bin problem. That's the question, and what I claim is that it's not better, but essentially this is the same when you're solving a max min. When you're solving a max min in kind of in what you're kind of in this framework that you're proposing, what you're doing is you're solving a two-player zero-sum, where you're solving the two-player zero-sum game of this problem over the strategy space where the strategy space is defined as kind of these epsilon balls around each data point. Okay, and I'll show some examples just in a second. Okay, that's a great question. So kind of from this mindset, right? Then we have like the adversary and the learner are playing a two zero-sum game where the strategies are randomization on attacks. This is by the adversary, and kind of retrain classifier. These are the strategies for the learner, right? And the utilities, right, are for basically the adversary wants to maximize the loss of the learner, and the learner wants to minimize her loss. Okay. So basically, this, as was just kind of proposed, right, a different way of kind of looking at this is basically as a robust classification. We can think about this as robust optimization, right? So in robust optimization, what we want to do is we have some sort of class of loss functions, this L, right? And what we want to do is we want to optimize some parameter. We want to optimize we want to minimize the max loss, where the maximum is taking over all loss functions from this class L, right? And we're interested in optimizing for some parameter. Makes sense. So kind of like some examples in adversarial machine learning is kind of a simple way of thinking about this is what I said is you can basically think of, you have like k, you can produce k different loss functions, right? Where each loss function is kind of is a loss function where you retrained on a given attack, okay? And another way is kind of to think about, I think this is kind of the formulation that you're asking about, is where basically we look at all possible perturbations around a point, right, and a certain ball around it. Make sense? Okay. So these, and there are other sort of, right, there are other sort of classes of L that you can consider. We'll talk about a few of them. And basically, I think that the bottom line is that ultimately we don't, given the fact that we don't know how to guarantee that we can even train neural networks, that we don't have any guarantees for even training neural networks, right? We can't give any guarantees for kind of training robust neural networks, right? And now basically where we're going is we're going with basically different techniques, right, based on different assumptions and different models, right, and kind of the way to sort of compare these techniques is oftentimes empirically, but we can still get some guarantees. Yeah.
Questions. You're talking about a loss that is an empirical loss computed on the training set. I mean that so this depends on the xi that you have in your set, right?
Yeah.
So if every attack is dependent on xi.
Every attack is applied. Well, yeah, every attack is applied on your data sets.
And here you want to optimize for when you say minimize the loss for the learner, you say minimize the empirical loss over the predefined set of xi. This
Minimize the loss over a given set of xi's. Yes, yeah, we're talking about empirical loss. Yeah. Again, because we don't have any, general we don't have kind of generalization guarantees. So, okay. Okay, so how do we? What are some methods for thinking about robust classification? So here's a simple observation. So if all your functions in L are convex, as they are in linear classifiers, then basically max L from this class is also a convex function. And then finding the min-max of L, it can be solved with convex programming. That makes sense? Right. So given that you have access, right, to max L from this class. And a lot of the a lot of the techniques sort of have this in the back of this is kind of the first step is in terms of intuition. Okay? So the main challenge is that in neural networks, right, the loss functions are not convex, right, and this is why we have to start making these different assumptions and using different techniques, right. So basically, we're going to talk about two different methods. One is adversarial training, and the other one is robust optimization when you have non-convex objectives. Okay. All right. So adversarial training does the following thing. Basically, what you do is you can think about this as adding points in a small radius around your points, right? Where these points are adversarially. Basically, what you're doing is you're applying an adversarial attack on these points, and then what you're going to do is you're going to train your model using something like stochastic gradient descent. So more specifically, the loss function that Goodfellow et al. Use is a convex combination of a loss function that of like the original loss function where you don't have adversarial noise introduced, and a loss function where you're introducing the adversarial noise to the point, right? And then you're just training stochastic gradient descent on this. So this makes a lot of intuitive sense, right? In both from both perspectives, right? One perspective is that what we said before, right? If the loss function is convex, then then you can just run stochastic gradient descent and optimize and optimize your loss function. But it also just makes intuitive sense in when you're thinking about what is the problem with adversarial noise and what's the problem that you're addressing, right? The problem with adversarial noise is when you have these sort of points, and now you're adding some sort of noise to it. You go across the decision boundary. So basically, what you're doing is you're doing some sort of regularization, right? Where you're making the decision boundary to be less more robust in that you're making the margins wider. Right, and which is basically what SVM does. Yeah.
How do you generate R sub x?
Okay, so R sub x is the random is the adversarial noise, right? And now, so I'm presenting good. So there are different methods. There basically R sub x is basically you use all the different methods that we talked about in the beginning, right? We talked about the fast gradient sign. We talked about the iterative fast gradient method, right? And then we talked about the deep fool, right? So basically, what you do is you take your favorite, way of generating adversarial noise, right? And then you retrain your model based on that. Cool. Okay, so for linear classifiers, this is the philosophy is that this is basically regularization. This is close to what SVM would do. The challenge, I guess, for us is to basically think, are we able to get provable guarantees for when we run stochastic gradient descent using this method, right? So again, for general neural networks, this is a hard task, but for things like true layer neural networks and other neural networks with specific activation functions, then it's possible that we can make progress on this question and actually prove that this is, that this adversarial training generalizes well. Okay, so now a different type of right? Okay. Oh, so this is just illustration of what's going on here, right? So you you kind of, this is what I was explaining kind of earlier. You just kind of robustify the points around you, and then you train the classifier. Okay. So a different idea, and this is maybe an idea that's closer to our community, is doing robust optimization for non-convex objectives. So the idea here is kind of fundamentally simple. What you do is you basically find the optimal strategy for the learner, right, against the adversary's attacks. Okay, so the idea is that you take your data and then you apply a certain attack on it, right, and then that gives you one classifier. And then you take the data again and you apply a different kind of attack on it, and that gives you a different classifier. You do that again, it gives you another classifier, and again, and oops. Okay, so so you basically have, as a learner, you generate all these different types of strategies by applying different types of noise, right, and generating a different classifier for every type of noise. Okay, this is the intuition behind this. So for simplicity right now, let's just sort of think of a case where we have a finite number of attacks, right? So like R1 through RK, right, that we can apply. And then basically for each one of them, right, we can basically retrain a model, right? We define a loss function, Li, that is basically the original, whatever your original loss function is, when you apply the adversarial attack on the data point. Okay. And now the goal is basically to solve the min-max problem, right? Which is basically finding equilibrium in this zero-sum game. Right? You have a finite number of strategies for the learner. You have a finite number of strategies for the attacker. Right? These are the different types of attacks. Right? And now your optimal strategy is to find this sort of an equilibrium in the zero-sum game. So again, the main problem is that all your loss functions, the ones that we care about in the ones that are used in deep learning, none of them are convex. Right? So the question is, what sort of guarantees would we be able to give in this sort of context? Right. So one simple observation is that all these loss functions can be trained well empirically. Right? We don't know how to prove that that we know how to optimize them, but empirically we see that that they give us some sort of high accuracy. And another observation is that whenever we have neural networks, because of their structure, we can basically train an ensemble of these loss functions well. Okay, so we can basically kind of gather these kind of different neural networks, right? And together, if we know how to train one and we know how to train another one, we know how to train both well. So kind of abstracting that, we can say that we have, with neural networks, what we often have is what we call like an alpha stochastic oracle. Okay, so kind of the formal definition that we can give is basically we can say, suppose I have like a distribution D over a set of loss functions. So I have an alpha stochastic oracle. If this oracle can basically return to me a solution that in expectation over the draw of the loss function, okay, based on this distribution, right, is an alpha approximation, right, to the actual optimum. Okay, meaning that basically for whatever sort of distribution that I have over neural networks, right, I will basically I know how to train a neural network that has some sort of alpha accuracy, okay? Which is kind of what we believe is often the case, right? So because neural networks do so well, so we can basically think of many tasks neural networks that are actually, they give us like something like 99% stochastic oracles. And the idea is basically to sort of kind of get rid of the fact that we don't have any, get rid of the fact that we don't have any guarantees for training neural networks. We push that to the alpha stochastic oracles, and then given that we push that to the alpha stochastic oracles, we can basically say, so what is the sort of guarantees that we can get, conditioned on the fact that we know how to train neural networks well. So basically using kind of the techniques of boosting, right, or kind of multiplicity updates, what we can do is whenever we have access to an alpha stochastic oracle, we can run a multiplicity update algorithm with t rounds, and what we get is we get a solution that's a very good approximation to the optimal min-max solution, right? So specifically, what we can do is we can find a solution theta hat right? So that the maximum loss over these functions on this theta hat in expectation is no more than alpha times the optimal solution to the min-max plus little error of like O of 1 that goes to 0 as t goes to infinity. Does that make sense? And kind of the way to do this is basically to proving this is kind of using the same techniques that you prove standard theorems in this for online learning. Okay. And now kind of when your parameter space is convex, then you can get rid of the expectation, and basically you can say that your the maximum loss is smaller than is no more than alpha times the optimal solution to the min-max plus this little O of 1 mistake. Okay. So this is nice. Whenever we have classifiers that are parametric, right? But you can also show this for kind of more generally. You can show this for a classifier for general hypothesis spaces, right? So whenever you have not functions but functionals from some hypothesis class, right, to 0, 1, then you can basically get the same guarantees, right, on basically on a hypothesis class or a neural network, right? And kind of everything that we said until now, we assumed that the strategies, right, of the learner were essentially finite, right? The strategies of the learner and the attacker were essentially finite, right? But if you're willing to assume that you have like some sort of structure behind these functionals, right? That they're specifically that their parameter is by some sort of weight W, and they're concave in this W, then you can actually show the same guarantees for these loss functions, even though you have like infinite strategies. Okay, does that make sense? So this is kind of like the furthest that we know how to push theoretical guarantees, right, for this this kind of robust classification. Okay. So this is this is kind of an assumption, right, that that your loss function is concave in this parameter W. But the fact that it's concave in this parameter W allows you to do this training of like the multiple weight updates. So kind of like the challenge here would be to actually show provable guarantees, right, for basically with weaker assumptions, right, about loss functions, right? So what happens when they're not concave in these parameters, right? Which is often the case with neural networks. So what can we show then? Okay. Just more generally, right? In this sort of area, what we have is we keep on using multiple weight updates, right, to do robust optimization. And kind of there are two kind of interesting phenomena. Number one is that when you look at the multiple weight update algorithm and you track the iterations, what you see that it actually converges way faster than it actually you require theoretically, right? And the question is why, right? So it sort of says that there is some sort of structure that we're not leveraging, right? And that we could potentially leverage, or some sort of assumptions that we can introduce that will tell us why it actually converges in as little as maybe like 5 steps rather than 1,000 as the theory predicts, right? And the reason why it's interesting and important is because running the multiple update algorithm is a pain, right? Now, why is it a pain? It's because if you think about what it does, basically you need to, in each iteration, you need to basically retrain a neural network. Okay? So now, if in each iteration you need to train a large neural network, like something like ImageNet, then you really want to know that you can actually finish your kind of the training of the robust classifier in a small number of steps rather than a large number of steps. But somehow, kind of another interesting question is, given that basically finding these best response oracles or retraining the neural network is the computational bottleneck, the question is whether we can do that somehow more efficiently, right? So kind of the naive method, and this is the only method that I know, is whenever people use multiple weight updates, in each iteration they retrain a neural network from scratch, right? The question is, do you really need to retrain a neural network from scratch given that in the previous round you've already trained that neural network with usually kind of very similar parameters, right? So is there some sort of can we somehow like initialize, right, the training from the previous step, right, and somehow cut the the cost of retraining the neural network in every step, right? If we can do that, then kind of it's theoretically interesting, but it's also practically very interesting, and basically it can make these methods kind of it could just make these methods kind of like very practical and fast and interesting.
Question?
Yeah.
Do you know anything about like between two different iterations, how far the solutions are they close to each other?
Okay, so that's a great question. Like so the question is like if we're running multiple updates and we have like in each step we have some sort of solution, can we give any guarantees on the distance between these solutions, right? So the kind of without any additional assumptions, the answer is the answer is no, right? You can basically show examples where you can have of course you have convergence, right? But you can show somehow like these kind of like oscillations. So we don't in general we don't, but kind of empirically everything that we've observed, there is some sort of convergence. You can see that these solutions somehow are close to each other and converge. So so it makes like perfect sense to kind of try to build around that. Okay. So kind of like those are the I think kind of like this is kind of like we're touching a little bit about kind of adversarial noise as a zero-sum game, and basically when Vasilis is going to talk about GANs, he'll kind of pick it up from this point, right, and talk about how training GANs is basically kind of how it's sort of like a more challenging than adversarial noise, and kind of like the additional assumptions that we need to make, and kind of how we train these GANs. Okay. An adversarial noise, kind of there are some additional topics that we haven't discussed, and this is kind of what I said in the beginning about this is now the 44 and a half, we're at the 44 and a half minute point. So everything that we kind of, two things I just kind of want to mention are black box versus white box, and then the last thing I'll talk about is randomized smoothing. So everything that we talked about is basically assumed white box attacks, right? So we assume that we have access to, in order to attack and defend against these attacks, we assume that the adversary has access to the actual, the classifier. Okay. But there are kind of interesting cases where we have models of black box attacks, right? So what are models of black box attacks? So in one case of black box attacks is when the adversary has no knowledge of the neural network or the classifier at all, right? And still tries to kind of generate an adversarial attack that fools the network. Okay, so in a paper by Liu et al. From 2017, what they did is basically they took 5 pre-trained neural networks, and what they did is they trained an adversarial attack, like kind of used the fast gradient sign method on 4 of them, and then used the adversarial noise from the ensemble in the 4 to fool the 5th one. And what you can show is that actually there is transferability in the noise. You can actually show that by kind of training on these 4, you can attack the 5th classifier, right, without without seeing it, right? So kind of an interesting question, right, is why is that true, right? So one can sort of imagine that you have some sort of model where you have classifiers that are drawn from some sort of distribution, right, and then you're somehow kind of like building an attack that's trained on a small subset of them that's somehow sampled from this distribution, and now to see whether this sort of attack can generalize, right, to a classifier that you haven't seen. Right? So this could be like an interesting question, or that we don't know how to solve. Another type of black box attacks, yeah.
When you say different classifier, you mean completely different architecture, or?
Yeah, completely different architecture, not completely different architecture. I mean, like, something could be, interesting is maybe, you can have some sort of parameterization, right, of this classifier, and maybe show that, like, if you have some sort of set of parameters, right, you can do a black box, right? You can kind of like train on, kind of classifiers where you have trained on like similar parameters, right? And then, right, you attack like a classifier with the same architecture, but like, again, just different parameter drawn from a distribution, and maybe you can show that. Maybe that's sort of like a kind of like an easier step, but we don't, but no such results exist, right? So this sort of phenomena of being able to take a, like a bunch of classifiers and attack a classifier they haven't seen yet is something that people don't know how to explain. And then kind of a different model for black box attacks is basically basically a model where you can basically you have access to kind of like you create a perturbation, and then you can see kind of like how the loss function reacts to this perturbation, right? You see the value of the loss function, right? So you don't know the gradients, right? But you can see the values, right? So here the challenges are, one is creating efficient attacks, but also you can sort of now imagine how do you extend these sort of like the results of zero-sum games, how do you extend that to black box attacks of this kind? Okay, and kind of like the final point that I haven't touched is on this technique of, technique of randomized smoothing. So this sort of technique of randomized smoothing is, the idea is that you're basically now retraining your classifier where what you're doing is instead of an adversarial attack, you're basically creating Gaussian noise, right? And outputting the decision of the classifier for a perturbed point. I think this is the wrong slide. So okay, so here are the challenges. Kind of like this sort of method is kind of like the latest and greatest, and kind of is kind of like the state of the art in terms of in terms of empirical results for L2 norms. And the question is, what sort of guarantees we can state for this sort of randomized smoothing methods? Okay. So that's kind of like this is the yeah, okay.
What about differential privacy?
As a defense mechanism?
Yeah.
For adversarial attacks. Okay, that's a good question. I don't know the answer. I don't know the answer whether I don't know the answer whether it's been tested and kind of and hasn't done well, or I have to think about it offline a little bit, but I don't know. It's certainly a kind of like a very reasonable approach, but I don't know. Yeah.
Sorry, so we don't know whether this method is good as defense against adversarial attacks. What is it good for?
The what? Sorry, the randomized smoothing.
The randomized smoothing.
Oh, it is good against L2. It's good against kind of attacks on the L2 norm. Kind of sort of their attacks are designed for L infinity norm, but this is kind of like one of the best defenses known for the L2 norm. Okay, good. So basically, what we're going to do is we'll take a short break, right? Vasilis, when do you want to start? Okay, so we'll take a 20-minute break, and then we'll come back, and Vasilis will pick it up talking about.